Hello everyone, how are you doing? Okay, so tired? A little bit? Yeah, a little bit. So today is kind of so let me start recording this, right? So she already started. Okay. So today I'm going to keep talking about reaction diffusion equations, right? So it's funny that it's kind of in mathematical terms it would be considered a bit complicated, right? If we wanted to go for all the mathematical aspects and so on, right? But then this is a computational course, right? So we are allowed to just ignore this and look at the solutions with the methods that we have already developed, right? And I think I'm trying to do this in a kind of a very relaxed way, you know? So you're going to see some nice animations and so on, right? And I hope it's fun, you know? Yeah? Okay, so today I'm going to follow more the tutorial, right? So we won't have as many new derivations and so on, right? So this is here, reaction diffusion equations. Let me put this over here. Yeah, so you remember this, okay? So before doing into that, right? So let me go back here, right? So what we did in the last class, right, is essentially that we started from a patch model that we then put the patches in a line, and then we said, okay, maybe if we make the patches very close together, from that we arrived at something that we essentially derived the diffusion equation, okay? Yeah, you remember that, right? And it turns out that this, the solution that we gave to the partial differential equation, that is reaction diffusion equation, right? Partial differential equations are equations that involve more than one independent variable, right? You have time and space now, right? So you have a density of population in terms of both time and space. So this is a partial differential equation, right? So and the solution to this partial differential equation was already written in terms of a system of ordinary differential equations. Yeah. So how did we solve these partial differential equations? I divided the space into many I would call patches, but it's actually many different regions, right? Subdivisions, okay? And each of them has a differential equation that is coupled to the nearest neighbors, yeah? So this way of solving this partial differential equation is actually one method to solve that, right? So this is called the method of lines, okay? I didn't call it by name before, right? But this is the famous method of lines, right? And this is, I think, the method, I think it's the simplest method for this kind of PDE that is actually efficient and nice to use in practice, okay? There are other methods, so you can use, remember that I talked about the Euler method when I first did numerical integration, right? So you can use Euler methods, you can use Runge-Kutta methods for people that know this stuff, okay? But for partial differential equations, this kind of method, even Runge-Kutta, those methods called explicit methods, okay? Methods that are, if you have no idea what I'm talking about, you can just filter out, okay? So this is for people that want to solve equations using different methods, okay? For partial differential equations, the convergency properties are usually very bad, okay? Very bad means that you have to take very small time steps, and this is very computationally intensive. So, so usually the methods that are most commonly used to solve ordinary differential equations, that are those explicit methods, they don't work very well for this kind of equations, for partial differential equations, right? Because they become inefficient, okay? Because they don't have good convergence properties, okay? So in order to solve these equations, it's better to use another type of methods that are called implicit methods, okay? So if you know about implicit methods, then these are the ones that you should go for if you want to implement your own your own solver for partial differential equations, not based on the method of lines, right? But this is much more involved in terms of learning how to do it and so on, right? So I really recommend sticking to the method of lines. Okay. Yeah, okay, so this is not so, I promised some fun, right? But this is not so fun, perhaps not, okay. So now what I want to do now is, okay, I want you to rewrite the program from yesterday, but in a slightly smarter fashion, okay? Because what we have done yesterday was, well, I had that migration matrix, okay? Yeah, I had that migration matrix, and it was an n by n matrix, yeah? So where n is the number of patches, right? Sorry, the number of subdivisions, okay? But if I want to have, remember that this number of patches, right, is an approximation for the continuous line, okay? So if I want my solution to be very precise, okay, or if I want to have the distribution of population, or the density of the population over space very refined, I need to increase a lot this number of patches, or this number of subdivisions, okay? So I want a very large n. So this matrix will become very large, okay? It will be like maybe 500 by 500, I don't know. And actually, I only do that because I want to sum the patch to the right and the patch to the left, right? So I don't actually need a matrix for that, right? So here I'll first show you how to do that without having to actually carry a matrix, okay? We can do that without the n matrix, okay? So let's do that. So first thing here, maybe it's better to turn off the light, yeah? Okay. So here we go. So here is exactly the same thing as yesterday, okay? So I put n equals to 5 here, so it's just copy and paste it, okay? Just to remember where we were, right? So this is the n matrix with ones in the diagonal above the main diagonal, below the main diagonal, right? With 5 patches, and I solved this using ODE int over here, right? So I just copied and pasted. I did nothing different from what we did in the last class, okay? And then I plot those populations here. You see that the initial condition is zeros, except for the first patch that is 10, okay? And then this decreases, and all the others increase in order, okay? Now what I want to do is, instead of, what I want to change is, okay, I want to change this part here, right? So because I'm using matrix operations to do this, and there's a smarter way to do that, right? So I want to subtract the sum of the columns, right? And I to sum m times x, okay? So let's see what this do, right? What does this do? Yeah. Okay. So let's take, for instance, let me take some x here, okay? Then let me print x and m, right? So let me do this step by step here. So this part here, this is x, right? So just put some numbers here, okay? And then this is the matrix M, okay? So there's 2 diagonals that we have discussed before, okay? So there are 2 parts to this calculation. There's the part where I subtract the sum on the columns times x, and the part that I do the matrix M times x, okay? That is the positive part. So the negative part would be this sum here, right? So the sum over each line, over each column, right? So what is the sum of this matrix? Let me print it again. What is the sum of this matrix over each column, right? It's just 2, okay? I have 1 and 2, 1 and 2, 1 and 2, right? The only exception is the first and the last patch, right? The first and the last will be just 1 because they are not leaving, so there are no patches to the right of the rightmost, the last one. There's nothing to the left of the leftmost patch, yeah? Okay, so there's only 1 in the borders here, in the first and last subdivisions. Yeah. Okay, so far. Okay, so of course I don't need it. I don't need a matrix. I don't need to sum the matrix. I just know that all of them will be 2, and at the borders will be just 1. Yeah. I don't need a matrix for that. Yeah. You know, because it's always the same value. Okay? So far so good? Now let's do the second part, right? So what we do in the second part is do this. We take M and multiply, matrix multiply by S, okay? And then we have this, right? So, yeah, let me print everything, right? So, like this. So I have this S, M, and then this part here is, what is this part here, right? This is 0, 1, 3, so it's this matrix times this vector, okay? So I take 0 times 1 plus 0 times 0 plus 1 times 1, 3 times 0, 4 plus 0, 4 times 0, 2 times 0, to get this 1 over here, okay? But actually this 1 over here, it only comes from looking at the neighbors of the first element here, that is just the 1, and multiply by 1, okay? And this 2 here, sorry, this 3 here, okay, what is it? I look at the neighbors of the second element here, there's 0 and 3, and I just sum them, okay? So I just sum 0 with 3. And what is this 5 here? I look at the third element and look at its neighbors. So I sum 1 with 4. You see? Yeah? I just take each element of the X array here, and for each element I sum the left neighbor and the right neighbor. Okay? Yes or no? Clear or not clear? More or less? More or less means I should go back, or more or less I should keep going? Is more or less keep going or go back? Okay. Okay, so yeah, and then the final term, what is the final term? The term that will actually appear in the equation, right? In the equation over here is this the sum of the columns times X plus this other term, right? So I just sum this part here times X plus the M dot X. Okay, so this is exactly what appears in the differential equation. You see, yeah, this is the same thing as over here. Okay. Okay, but then let's try to do this in a different way, right? So what do I do? So for the first, you see that the borders, they're a bit more complicated, right? Yeah? Because in the borders, I have to multiply by 1 instead of by 2. And at the borders, I only have a single neighbor. I don't have at the left, I don't have the left neighbor. At the right, I don't have the right neighbor, right? So maybe let's look just at the elements in the middle, okay? For the elements in the middle, for the 1, 3, and 4 here, right? For, yeah, they are always subtracted. I always take them multiplied by 2 and subtract, right? So you see that the sum over the columns here is minus the sum over the columns, and the sum over the columns in the middle here is always 2. So I just take minus 2 this times the elements in the middle, you see? What are the elements in the middle? You see, I have a slice here that takes out the first element. I start at the second, and I stop before the last element, okay? So these are, I'm excluding the left and the right end, okay? The first and the last element, okay? And now, okay, if I print this stuff here, what is it, right? So, so let me print just this right, so what is this? So this is just, you see, you have the whole array here is 0, 1, 3, 4, 2. If I take only the middle here, I only have 1, 3, 4, right? So, what did I do here? Yeah, only 1, 3, 4, you see? So I just got the elements in the middle. I'm going to do minus 2, the elements in the middle, and then I want to take the neighbors of these guys, okay? So what are the neighbors of these guys, right? So if I have to, what do I have to sum to this 0, 1, 3, 4, 2, right? So I want to sum, for the 1, I want to sum 0 and 3, right? So I want to sum, to each of them, I want to sum the left neighbors. So I have to take 1, 3, 4 and sum the left neighbors. What are the left neighbors of 1, 3, 4? Is 0, 1, 3, right? And then I have to sum the right neighbors. The right neighbors of 1, 3, 4 is 3, 4, 2 in that order, okay? So you see, the left neighbors will be beginning at the start with 0, 0, 1, 3, 0, 1, 3, and lefting out the last two elements. And the right neighbors will be 3, 4, 2. It means I skip the first two elements and go up until the end, right? So this here, so let me print this, right? So this here, so these guys here, right? So they are, let me print them. So these are the left neighbors and the right neighbors, okay? Let me print both of them. Oh. So, you see, I have 1, 3, 4, and then the left neighbors are 0, 1, 3, and the right neighbors are 3, 4, 2, right? And then I just take minus 2 times that, I sum this thing, the left neighbors, I sum the right neighbors, and this is exactly what I was doing before. Yeah? Make sense? Yes or no? And so this part here, right? So let me run everything up to here now. So trying to go step by step, right? So for now, so we have this final term here. You see that with that sum here, I already have the URET values for the middle, you see? 1, minus 1, minus 3, you see? Yes or no? Yeah? Okay, so with that, there's only remaining now the borders, okay? The first and the last term, okay? And now the first and the last term, what do I do? Now I want to do exactly the same as before, right? But here, I kind of, I have thrown out the borders, right? So in order to not throw out the borders, what I do is I define a new vector. This new vector will be, I already have this minus 2 times x here, that is over here. And I take the middle range here and sum these two guys, right? And sum these two guys. And now I have to go back. So this now has the same shape as x. Because the problem of doing this here is that I excluded the first and last points, right? So now I'm not excluding the first and last points, but I'm setting them separately over here, you see? So it's saying that the first element is just minus itself plus the first neighbor. And the last one is minus itself plus its neighbor to the left, okay? Yeah, so I'm doing them separately because they're more complicated, right? Yeah, and if I do this and now I print this resulting thing here, I get this thing here that is the same as we had before, you see? So doing this part here, right? Doing this part here is the same as doing this, okay? It's the same as doing this. Okay, this looks more complicated because it uses more lines, but actually there are less operations, right? Because here I have to do a sum over an n by m, sum over the columns of the whole matrix, or all of the columns, and then I have to do a matrix multiplication. Down here, I just had to multiply a single array by 2, sum 2 other arrays, and then change a single number at both ends, right? So it's a lot less operations than doing the whole matrix multiplication. Now, imagine multiplying a whole 100 by 100 matrix compared to summing just an array of 100 numbers twice, you know? So this, even though it looks a lot more complicated and more lines and so on, there's a lot less computation than this stuff here, okay? Yeah, yes or no? Are you convinced about that, or are you just happy to accept and move on? Okay, let's just do that, and yeah, okay, this is not as fun as I promised. Okay, let's start with the fun, right? So let's go. Okay, so I'm going to do this in this way, right? So, and what is missing here, right? What is missing is that, remember that for the diffusion, right? I had this n here, right? And I would multiply this migration rate here by some constant, okay? That is the migration rate. But remember that when we derived the reaction diffusion equation, right? Actually, this second derivative here had to be divided by delta x squared, okay? And my g was actually a constant, right? So besides doing this stuff here, now I won't have a migration rate, right? Now I want to include not migration rate, but diffusivity itself, okay? So in my equations, now I'm going to write a new equation here, right? So, and you see that now I don't receive M anymore. I don't receive the matrix M. I just receive the diffusion constant, okay? And I also need to know the size of the spacing between each point, okay? And now I do this whole thing as I did before, okay? This is exactly copying the stuff over here, okay? Copying the stuff over here, so it's exactly the same, okay? And now this part here, I have to divide it by delta x squared, okay? And multiply it by the diffusion coefficient, okay? So this g over gx squared plays the same role as the migration rate that we had before, right? So the migration rate is diffusivity divided by delta x squared, okay? Yeah? But now I don't need a matrix M anymore. I just need to know what is the diffusivity, what is the size of the subdivisions that I have, okay? Yeah, nice? Nice, okay, so let's solve the same thing with that, right? So I call this function here FKPP, right? Because this equation here, where you have the logistic over here, right? This is all the Fisher-Omoorov, Piskunov. What is the name of the fourth guy? Another Russian guy, sorry, forgot his name. Yeah, I usually remember, yeah, Silas remembers, right?
Petrovsky.
What?
It's another Petrovsky, isn't it?
Sorry?
Petrovsky?
Petrovsky?
I guess it's another Petrovsky.
Okay, Petrovsky, Piskunov, or Piskunov, Petrovsky.
Yeah.
Okay, don't know the order either. Okay, so Fisher-Omoorov, Piskunov, Petrovsky. Okay, yeah. So this is from the time where I think Soviet research was going on in parallel, and but they didn't communicate, and then pretty much everything in the Western science was done first by some Russian. Yeah, so these names became confusing, right? So I think in the ecology and evolution, most people know the work of Fisher-Omoorov mostly, right? So even though Omoorov is also Russian, but his work was earlier, right? So it's from the 30s, yeah. So, well, okay, but then, so this is FKPP equation, right? So, and then I have all of this stuff here, right? So this whole thing here is to calculate the second derivative term that I multiply by g divided by the gx squared, and then I just sum here the reaction term, okay? The reaction term is just as we had before, right? R x 1 minus x over k, okay? And now I'm looking at homogeneous space, right? So now I don't have to have that R and k are vectors, okay? They are just numbers, because I'm assuming that the space is homogeneous, okay? So the growth rate at each point in space is the same. The carrying capacity at each point in space is also the same, okay? Okay, and now let's try to do this with some numbers, okay? So let's put the number of subdivisions equal to 50. I'll try for now to look only at diffusion, so I'm only setting R to 0, okay? So I won't have growth, I won't only have diffusion. Now the diffusivity I'm putting equal to 1. And now, you see, now we are looking at an actual spatial region, right? So I have to know the size of this space, okay? So I'm going from x equal to 0 until x equal to 4, okay? So this would be 4 meters or kilometers, depends on the species, okay? So for maybe 4 centimeters if you're looking at bacteria, yeah? So yeah, depends on the scale depends on the units of space as well, okay? And this is important because G itself has dimensions of space, okay? So when you divide it in 50 subdivisions here, right? So it changes your dx here, right? So what is this dx here? It's going to be the size of the spatial range that you have divided by the number of subdivisions, okay? So you have to know the actual physical space that you want to model, okay? Okay, so I set this up, okay? Now X will be my spatial grid. It goes from 0 up to L in n subdivisions. Okay. I think there's actually a bit of a mistake here, but I will talk about this later. Okay. Now I set the time steps here. I give you an initial condition, so I'm going to put everything equals to 0, except the first patch here, the first point here that is equal to 10, and I'm going to solve this. Okay. And just see here that I have the same parameters here, R, K, G, and Gx here is set to L over n, okay? Yeah, I could already talk about this mistake here, okay? But yeah, let's do that and then yeah. So what is the error here, right? So if I look at the array X, okay, you see that the spacing here is if I print this and I print L divided by M, okay, you see, it's not the same. You see? Here I have a spacing that is a bit larger than 0.08. Why is that? Link space divides, if I have, for instance, let me show on the board, right? If I have if I go, for instance, from 0 to 1, and I say that I want n equals to 5, right? So I need to have 5 points. So I have to have 0, I have to have 1, and I need another 3 points in the middle, okay? How many subdivisions I have here with 5 points? 4 subdivisions, not 5, yeah? Okay, so when I have n equals to 5, I'm actually dividing the space in only 4 pieces, okay? Yeah? Okay, so this is why this is a little bit wrong, right? So with large n, has a small difference, but it's better to do stuff the right way, right? So instead of saying that my gx is dividing by m, right? It's better to say that my gx here, I have to divide it by m minus 1, right? Yeah? So this, oops. I have to divide it here by m minus 1, okay? Yeah, so this is the correct approach, right? So if I do this now, I think this gives me now the right, you see? This gives me now the right size of each subdivision, okay? Yeah, clear? Okay, so okay, so let's run this again, okay? And now let's plot the populations over time. Well, this is a mess, right? Yeah? So I have 50 different lines here. The first one started with 10. All of the others started at 0. This is really bad to see anything, right? Yeah? Really bad, yeah? Because now what I actually want to see is not each population. I want to see the distribution over space. I want to see the density over space, okay? So instead of plotting it in terms of time, I want to plot it in terms of space. Okay, so what do? I can plot, I have X, that is the grid here. Okay, I have the grid over here, X. Okay, and I want to plot the solution, right? The solution U now. I'm going to change notation here. I was using X for the solutions, right? But now X, I want to say that X is space, right? And now I'm using U for the solution, that is the density, U as a function of X and T, okay? So I will have U, the solution, in terms of X, okay? So I take each line is a point in time, okay? So this is time 0, time 1, time 2, time 5, time 10. Not actually 10, right? So the 10th position, so my times go from point 2 in point 2, right? So this is actually at time, at time 0, at time 0, 2, at time 0, 4, at time 1, at time 2, right? Yeah? Okay? Depends on the time step, yeah? And I'm going to plot then over space, okay? And then if I plot then at each different time, I can see how this changes over time, yeah? So this is what it looks like. So at 0, I have the initial distribution, this is 10, and all of the others are 0, okay? And as time goes on, okay, I only have diffusion here, right? So I see that the populations are becoming more and more homogeneous in space. Okay, maybe let's not plot the first one because they are population times 0 is enough too large, right? So you see, so this is at time 1, then 2, then 5, then 10. It's becoming more homogeneous. Okay, so if I plot the last one, the very last one, right? So it would be like this. Okay, the last line. Yeah, so I just take -1 over here. Okay, the very last one is pretty much a constant line. You see? Yeah, so all the population is completely spread out, evenly spaced, evenly distributed over the whole region. Yeah, nice. Okay, so now let's animate this a bit, right? So what we're going to do is, well, it would be much nicer instead of looking at these lines here. Okay, just see this density, this population density in the y-axis as a function of the space, of the position x, changing over time, right? So it would have an animation, right? Yeah, it would be easier to look at the solutions, yeah? So there's some recipe here to do that, right? So let's learn how to do that. So I have, inside Matplotlib, I have a submodule called animation, okay? And then in order to do an animation, I have kind of set up the figures and the lines that you're going to use and so on. And then you have to have a function that updates the animation, right? That is going to draw each frame of the picture, you know? So, yeah, okay? So what do you do, right? So you start creating a figure, you create a subplot inside this figure, you set the ranges in the x-axis, in the y-axis, you put on the labels. Yeah, maybe let's also include, I think it's set grid. I think set a grid over here as well, a title, and then I want to have a line that I don't know yet what it's going to have, so I'm putting here an empty line, okay, an empty data, just 2 empty lists, okay, but I can say that it's going to be blue and it's going to have a line width of 2, okay. Okay, and now you see that usually when we plot, right, when we plot stuff, we just plot this stuff, okay. I don't care what this function plot returns. Yeah, I don't care because I'm not going to use this thing anymore, right? But now we want to keep updating this, okay? When I want to update a line, I have to have the object of the line, okay? So this plot here returns a line, okay, a line object, and then inside the function that draws each frame, I change the data of that line, you see? So for each time, for each number I, here the number of the frame, I'm going to change the data of the line to plot the solution. Yeah, I think it's better to write like this. It's the same, but it works like this. Yeah, to change which point in time I'm going to use. Okay, so that's the first frame at I equals to 0. I'm going to plot the initial condition. Then at the second one, I plot it at time 1, and then at time 2, at time 3, and so on. I'm changing for each frame the data that I'm using. Yeah? Does that make sense? I'm also changing the title to tell me which frame I'm looking at. Okay, this is just the number of the frame. Okay, and then I have this function here that I don't want to go into too much detail, right? But what do I have to pass to this function here, right? So I have to pass the figure that I set up over here, right? This function that updates, that draws each frame, how many frames I want, right? So for instance, I have 100 points in time. I want to say that this has to have 100 frames, okay? And finally, the interval between each frame, right? So if I put a large number here, it means that it waits, I think this is in milliseconds or something like that. This waits a long time between each frame, so the animation goes very slowly. If I put a small time here, a small interval here, it means that the animation is very quick, right? So it goes very fast, okay? It's usually better to do something intermediate so that you have time to see what is going on, but not so so slow that it's end up boring, right? So, and finally, bleed is just an optional parameter to tell whether to redraw everything each frame, or if you can just redraw the things that are changing. I'm not so sure that this is useful, but I copied the recipe, so this is in the recipe. So I got some error. There's no grid in this. There's no grid? How do I set up a grid? Maybe it's not set to grid, it's just grid, yeah. Okay, here, okay. And now this anim variable here contains the information necessary for the animation, right? What I have to do now is I have to display this animation. Okay, so there are several things that I can do with this object. There are some functions that take this and transform this into a video file, MPEG file, or GIF animation, or some other stuff that I can download and use, right? But it can also display it directly here using IPython display HTML, you know. So So I'm just using this code here to display it directly inside the notebook. And let's see what happens here, right? So, oops. Oh, it didn't fit here. So maybe let's go back and decrease our figure size a bit. Yeah, so maybe 10 by 5 is enough. Or maybe 10 by 5 is already too much. Maybe 8 by 5, yeah. It didn't fit here. But yeah. Yeah, it wasn't very funny, right? Because the scale is once again, yeah, maybe let's change the initial condition. Instead of starting at 10, starting, well, it's not going to work. Or maybe the widening here, instead of going to the maximum, let's stop it only at, I don't know, 4, right? And see if this is a little bit nicer to look at. So this is just to make a better visualization, yeah? Too fast? You see what is going on or not? Or is it too fast? Yeah, it goes very quickly in the beginning because you have a high initial condition over here, and then it goes down. Maybe I stop at half actually, the range here. So where is it? Yeah, 0.5, and now it go a little bit slower over here. So maybe 40. Yeah. So this is just playing a bit with the visualization, right? So. Now it's nicer, right? Yeah? So you see the frame here tells me the time. Okay? Yeah? Nice? So we can see what was going on with our solution, right? It starts like this, and then it converges to a constant solution. Nice? Yeah? Okay. Sorry? In the frame here, I put an interval of 40, and I changed the Y lim here to be only up to 1/2, okay? And also because I am using a very large font size here so that you can see what I'm doing, I had to also decrease the figure size. I think 12 by 6 was okay. It's probably going to be okay on your own computers, but then over here I decreased it, okay? Okay, good. So now, time for some exercise. I want you to run this model again, but now, until now I was looking only at diffusion, right? I want you to now include also growth in your model, okay, growth. And then with growth rates of 1, I want you to use a much larger range, okay? Try to use L equals to 20, and a slightly smaller diffusion, okay? And I want you to look at the video of this, of the animation, and tell me what does this do, right? So, yeah, your turn. Yeah, I forgot to ask, do you have questions? This is pretty much just a recipe, okay? But do you have questions? Are you good? Okay. Start this. Okay, so let's go for the solution, yeah? Okay, so first thing is let's copy the ode, all of the odes over here, okay? So let's take this thing here. Okay, now I want to set R equals to 1, G equals to 0.1, L equals to 20, and time going up to 40, yeah? Okay, something else that I want to do, I think it's okay. And now let me copy also the plots, okay? So this plot is kind of weird, but let's see also how it goes. Oops, forgot to copy. Now the animation part. Okay, so all the odes is over here. So let's do it, right? So I start solving the equation itself, okay, with the different parameters that I specified over here. Okay, so far, yeah, just copy the ode and change R, G, L, and T, okay? Just change the parameters, okay? And now this plot here is confusing, right? This plot here is confusing, but let's see what's going on, right? So this is what's going on. So this blue line is the first patch. Okay? So it is the first the one at 0 to 0. So I start at 10. It decreases a bit, and then it goes back to. Why does it decrease? Because it is losing population to the neighbors. Okay, the neighbors are all set to 0, so it's losing population faster than it grows, right? So it decreases, but then it goes back to 10 because 10 is the carrying capacity, yeah? Is the carrying capacity, okay? And all of the other ones, they start at 0, but then they have some population getting there, and they are starting to increase, okay? So the first one starts decreasing right away. The patch that is a little bit farther takes a little bit more time for the population to get there, and then for it to start growing, and so on and so on, okay? So until the very last patch, right? So the one at the right, it only reaches the carrying capacity close to the end of the simulation at time 40. Okay, so this is what this plot means. You know, it looks at each point in space and see this over time. So in the x-axis here, it is time, not space. Okay, so this is why it looks funny. Okay, yeah. So this is time, not space. So, but what we actually want to do that I think is simpler to understand is the animation. Okay, so we do exactly the same thing, but now let me put this at u.max. That, okay? So u.max is going to be 10, right? So because this is the end capacity. Sometimes I do this, right? So I do 10% more to be able to see the top line. Otherwise, the top line reaches the end of the plot, right? So I think it's a little bit better to see, okay? Not the minimum, because the minimum is 0, and okay, 0 is, yeah. Okay, so the rest is pretty much the same, okay? Not pretty much the same, it's exactly the same, right? So I go back to 30 here in order to not be so slow, right? And now let's plot the animation, okay? So what does this animation look like? Yeah, here it is. You see, I start with population only at the leftmost part. All of the rest is 0. Then it spreads out and grows and grows and spreads and grows and so on. Okay, so this is an invasion front, right? So this is an invasion front, or this is not exactly a wave, okay? Because what is a wave usually? A wave is something that goes up and down and moves, okay? But this doesn't go up and down. It only the thing is invading, right? So the tail over here stays up here at 10, okay? It keeps increasing carrying capacity over the whole space, okay? Of course, if I had more space to the right here, right? If instead of L equals to 20, I put something going to 50, it would continue increasing, yeah, until infinity, okay? Yeah? Good? So another way of looking at this is that if you look at each point in X here, right? So I look at this one. It's close to 0 most of the time, and then at some point in time, it increases, okay? And then it goes up, okay? So what we're actually doing, of course I plotted a line because a line is much nicer to see, but a different way to look at this is remember that we actually don't have a full solution in space. We divided space in 50 points, okay? So instead of plotting lines here, I could say that I go here, I change the line style to use points. You remember that, to use points? Yeah, so instead of just having blue, I put a point here, right? So if I do this now, okay, I see that all this line stuff here is actually an illusion, right? So yeah, because what we have is actually 50 points in space, okay? And they are going like this. Nice? What? The code. The code was, I just changed it in the line here. When I defined the line here for the animation, I put a dot here to tell it to use dots instead of lines. Yeah? So, yeah, so now you see what's going on. Yeah? So I'm solving the equation for each of those points over time, and I'm plotting all of them together. And since I plotted with lines, it looks like I have the density over space, but actually I only have the density at 50 points in space. And I just draw a line because, yeah, right? Because it's, I want to really get into this illusion, right? But actually we know that it's just an illusion. We don't have continuous space. We have, yeah? But now the animation is doing another illusion with us because it looks like it is continuous in time, but it's not continuous in time either. I have discrete points in time. So if I want to see that this is also an illusion in time, I just increase the intervals here. Okay, so let me put a large interval. Okay, now this takes a long time, sorry. But the continuity in time is also an illusion of your mind, okay? Because you only have discrete time steps, okay? So, you see? You don't have all the times. You see, now it's easier to see that you only have certain times, yeah? Yeah, questions, comments? Yes. Mike, please.
I just want to know why did you add this 1.1 multiplication before the U max? I didn't get it.
Okay, so let's go back a bit. Where was it again? This thing here. Okay, because if I just put U.max, it means that the Y range goes from the minimum to the maximum. The minimum is 0, and the maximum should be 10, okay? It means that this plot here goes from 0 to 10, instead of 0 to 11. And now, if you have done this in your computer, you see that the line, it gets stuck in the top here. It kind of looks a little bit worse, you know, because it's nice to see the line and not have the line right on the top here, you know, right over here, you see? Yeah, just should be a bit nicer to see, you know? Yeah? Okay. Nice, so now we have an animation, and with you we have a short interval and plot with lines, we have an illusion that we solved our equation in continuous time and space. But now, with larger intervals in between frames and plotting dots, we see that this is all an illusion, right? So we are aware of what we are actually doing behind the scenes, you know? But of course, for presentations, we never do this, right? We always do the other one because they look like, wow, we are so smart, right? Yeah? Yeah? Right? Okay, good. Nice. More questions, comments? Something else? Okay, so let's move on, right? So let's move on for new stuff here, okay? So, okay, so the first, the thing we have done before, right, is, it was like this. So let me use here the board a bit, right? So let me, yeah, over here. So, so we had this, right? So we had patches, right? So we had patches, just like this. Let me redraw this, right? So we had patches, and yeah, so we had something like this, several patches, and I told you that, okay, this exchanges individuals with this guy, and so on, right? So you had something like this, okay? And this for patches was okay, right? So when we thought about it in terms of patches. But now what we're actually modeling is something like I have a continuous range, homogeneous space here, that is a continuous range from 0 to L, okay? From 0 to L. And I'm just using the idea of patches because actually I want to solve this equation by discretizing it into small subdivisions, okay? But now what happens at the borders, at 0 and L, okay? The way we wrote it here, you see that the leftmost patch and the rightmost patch, it didn't lose anything to the outside. So all of the population here, it never leaves this region, okay? You never leak population to regions outside this region, okay? Yeah, okay? So we don't have flux to the outside, right? Yeah, even if you are here at the very edge, right? Yeah, at the very edge, we are saying that individuals at the very edge migrate to the right, but don't migrate to the left, okay? Yeah, so this is what we are doing here. These are called, when I don't have migration outside, this is what is called no flux boundary or reflective boundaries, okay? Reflective boundaries. It means that an individual that arrives here, it doesn't go through, okay? It goes back. So think of an aquarium, okay? The fish doesn't cross the boundary, okay? Yeah? An aquarium. Yeah, sure. So this is kind of closed for the population, okay? Closed. You never lose individuals through the boundaries, yeah? But of course, in real ecological systems, sometimes you have boundaries. You are interested in modeling a certain region, but the population is not closed, okay? It can live through the boundaries, okay? It can live through the boundaries. Okay, what happens in that situation, right? So we're going to look at another type of the other extreme example of this is that an extremely hostile boundary. That is, individuals, for instance, if I have something like these patches here, individuals are leaving to some thing over here, and this is the void. Okay, this is the void. Individuals that live here never return. Okay, they never return. Okay, either here or here, right? So there are migration to outside this region here, and individuals that live never ever return. Okay, so these are what is called extremely hostile boundary conditions. Okay, so these are the topic. So these are called boundary conditions. Okay, so things that happen at the boundaries of my habitat. Okay, why are these all hostile? Because essentially, how comes? Yeah, you think if you are very, you don't want to talk about this, you just say, oh, individuals never return. Another way to think about it is that individuals just die once they step out of the region. Okay, so think about this as as I don't know, some forest region that is completely surrounded by roads, you know, so yeah, something like that, okay? Or for instance, we use it to think about this institute like this because it didn't have any way to cross for a pedestrian anywhere in the whole block, okay? So you step it and you were run over, you know, so yeah. Nowadays there are some ways for pedestrians, right? But that a few years ago there was none, right? So yeah. Okay, yeah. So these are now mathematically you can express this in the following way, right? So I'm not going to go into too much detail, but I want you to have some idea where this comes from, right? So a no flux or a closed or reflexive or reflective? Sorry?
I think it's reflexive.
Reflexive, yeah.
No, I think it's reflective.
Reflective. Yeah, I'm not completely sure. Reflective. Yeah, like this?
Reflex is about reflexes. Reflect is about reflective. Nobody got it.
Sorry, I didn't hear anything. Sorry.
Reflex is about reflex.
Yeah, true. Yeah, you're right. Yeah. So it's reflective. Yeah, okay. Good. Closed or reflect or also no flux. Okay, no flux boundary conditions. Okay, so this here, how do you express this? Essentially, they're saying, okay, I have at the border something that doesn't change, right? This is similar to being closed. Essentially means that this guy at the border is not losing any individuals, okay? So you can think of it as in the sense of if you have something at the left of it, it's always as if it has the same population as itself. You see? Yeah. So if you were having, if you were to simulate this as a kind of a different patch here, right? So I have a patch that is a special patch, okay? And I'm going to say that if this never loses an individual, it is as if the last neighbor over here, if this and this, they are always the same, okay? They have the same value. The influx and outflux has the same values, okay? In order for this to happen, the population here has to be the same as the population here, yes? So the input and output here, the influx and outflux from this patch to this patch is the same. Do you agree with that? Yeah? So if I have the same population here and here, right? Then the migration from here and to here will be the same, okay? Yeah? This means that if I'm looking at going now for delta x going to 0, right? This means that at the border, the population has to be, there has to be a straight line, right? Yeah, constant here. So it means that mathematically you express this boundary condition as if I have now the density u, right? Density u as a function of x and t, right? It means that the del x at x equal to 0 is 0. The derivative of u with respect to space is 0 because this is f a constant here, okay? Yeah, does that make a little bit of sense? Yeah? And you, of course, are going to do this in the left, x at x equal to 0, and also at x equal to L, okay? So this is the mathematical expression for no flux boundary conditions, okay? You're going essentially to say that you don't have migration outside because the patch that would be just outside has the same population as the inside, okay? Makes sense? Yeah, so of course if you don't go into a lot of detail, you can just remember that this kind of boundary condition is written like that. And the other situation is what I just told you here, right? So if I have instead Hostile. By the way, maybe I should, yeah, maybe I should also give you the technical term, right? So these are also called Neumann boundary conditions, right? So, yeah, yeah, yeah. These are also known in literature, or mathematical literature, as Neumann boundary conditions. Another kind of boundary condition then is hostile, or absorbing boundary conditions. Right? So why absorbing? Because once the population lives, or individual lives, it never comes back. So it is kind of absorbed and never comes back. Okay, so these are absorbing boundary conditions that are also known as Dirichlet boundary conditions. Okay, so these are 19th century mathematicians, right? So Dirichlet boundary conditions. Okay, and for this we all had already thought about it, right? So it's as if all the population just leaves and never comes back. Okay, what happens? You have a kind of special patch right at the edge. The population leaves, but you have no one coming back. Okay, no one coming back. So it is as if this special patch at the border here has zero population, has always zero population. It receives individuals coming but returns none back. Okay, so now the density of this guy here is zero. Okay, so I'm going to say that for this kind of boundary condition, we have that not the derivative. We are going to set that u, the density at z0, 0 is equal to 0, right? And the same thing for at the other boundary, okay? At u at z0 is equal to 0, okay? Okay, so these are the most common ones. You can also do something intermediate. I'm not going to talk about this much. Intermediate things that are, well, boundaries that are partially reflective, okay? Partially absorbing, partially reflective, and then you're going to have, instead of del u del x to 0 or u equals to 0, you have that there's a proportion the derivative and u over here, okay? And then you have a partially reflective boundary, okay? But I'm not going to go into that, okay? Okay, does that make sense, people? So this is the mathematical expression for this stuff. But now I want you to see how we implement what we have done so far was with this type of boundary condition here, right? And what we saw is that if we have just diffusion, with just diffusion, the total population doesn't change, okay? Because there's no population leaking from outside. But if we use this one here, then we have population leaking to the outside, okay? So let's try to implement this, okay? Questions? Questions so far? So let's see what happens in the computer, okay? In the simulations. Okay, so okay, so what is going to change now? All of this stuff in the middle is going to be exactly the same. The only change is what happens at the first point and the last point, right? So all of the code is exactly as before, except remember that you have to take special care here with what happens at the point 0 and the point -1. The first and the last one, we had it going out of this patch, -1, and +1, it receiving individuals from the right, okay? Now it's almost the same. It is almost the same. So remember this stuff here, right? It's almost the same, but now there's a 2 over here. You see, because now you have individuals also living to the left that you didn't have before. You see, so it's exactly the same, but now there's a -2 here instead of a -1. Yeah? So that's the only difference. You have some individuals living to the left at the left-hand side and to the right at the right-hand side. Yeah? And they live to where? They live to nowhere because they are not modeling outside. You are losing population in this region. Okay? Questions? Comments? So let's see what happens here. So now I'm using, once again, I'm putting r equals to 0 to not have any growth, only diffusion, okay? I think I had this bug over here. This should be n minus 1, right? So, where is it? So this is here, this is, there's a missing parenthesis. And now the initial condition is, I'm changing my initial condition. Now I'm putting everyone equals to 1 initially, okay? So the initial populations, all the patches, all of the space has a density of 1, okay? And I'm going to see what happens, okay? So let's do this. I'm going directly to the animation. I'm going to put 1.1 again here because I think it's better. Let me go back to 8 by 5 so that it fits in this screen here. And I think that's it, okay? So let's see this animation here. So I start, so I start with everyone equals to 1. Let's see the animation now. Okay, you see, I start with everyone equals to, this is too fast, right? So maybe let's put more time here between frames, yeah? You see, is it still too fast? Or can you see what's going on, or is it too fast? I have also playback speed, right? So I don't have to run everything again, right? So let's go to the beginning. You see, so I start, I start, you see, I start with everyone equals to 1, and then I quickly have everyone going down at the borders, okay, because they're losing individuals at the borders. And now, as time goes by, I have ever less and less and less individuals. And the ones in the middle are the ones, the last ones should decrease, right, because they're farther away from the borders. Yeah, but they are sending individuals more to the left or right, and these are eventually reaching the border and leaving the patch, right? And so eventually, the whole population goes to 0, right? Because I don't have any birth. I only have migration here. I only have diffusion, right? They're just moving. But if they're moving, they are eventually going to reach one of the borders, and they leave and they never return, or they die, or whatever, and then my whole population is extinct, okay? Yeah, makes sense? Okay, so now of course, so there's always going to be extinction if I only leave a boundary condition, absorbing boundary condition, with no growth. But then if you also have growth, right, if I have a growth rate with logistic growth and so on, this is going to be compensating for these loss of population at the border, right? I have growth also, yeah? Does that make sense? So if I have growth, maybe the population doesn't go to extinction, right? So I want to do, now I want you to work on this again, right? So I want you to now take exactly the same parameters as I have here, okay? But now put r equals to 1 again, okay? And keep the other parameters the same, okay? And see if the population survives, okay? And see if the population survives. And then I want you to change the size of this region, okay? Change L, change the size of the region, and see what happens, okay? And then we are going to find something really interesting that is called the critical patch size, okay? I want you to find what is the critical patch size, that is what is the minimum size of the habitat so that the population is able to survive, okay? Good, so this is exercise time, okay? So time for you, we don't have a lot of time, right? But then, yeah. But then you can also play later, yeah. Questions before? Questions? Yes. Where's Mike?
It's something you explained it very early. I still have not understand this whole matrix plane. Actually, this is about the function itself. When you traded the m dot and the m sum to the shifting
when I shifted
arrays.
the arrays, yeah.
I didn't understand that at all, and I still cannot understand.
Yeah, okay, I think for that is, I can more or less repeat what I told you, but I think it's easier if you try to play with the arrays a bit, you know, like, and see them, you know, or maybe take a larger array and see by hand, like try to do the calculations by hand for a very small case, okay? So, and you'll see that you're just summing one array with another array. You see, it's just a matter of looking in detail, step by step, what the computation is doing, you know? So, yeah, I'm afraid I don't know any other way to explain it other than what I already told you, you know? So it's a matter of going step by step and seeing, well, this matrix multiplication is doing this, but this is exactly summing this array with this array, you know? So, yeah, because you only have 2 elements in each line of the matrix, you know? So all of the others will be 0. Yes?
Could you do the same with, I don't know if this is the right term, but with 3D matrices?
3 dimensions of space or 3
Yes.
dimensions in
Yes,
the sense
of
of time
space.
and 2 spatial dimensions? You can, of course, and you can go further, right? So what is
Yes,
doing?
time
This
and
is
2
something that if I
dimensions.
had more time, I wanted to talk about. But you can do the same thing here for more spatial dimensions, right? So what is going to happen in more spatial dimensions, right? So now your function u, the density, will be a function not only of x and t, but also x, y, that is the second spatial dimension, and t, right, in time, right? And then the equations will be pretty much the same. The main difference is that instead of having the second derivative in x, you have the second derivative in x and y as well, right? Plus the second derivative on y, that is what is called the Laplacian, okay? And then when in terms of numerical computation, instead of having individuals leaving this patch, exchanging individuals with left and right, you have individuals that exchange points in space, exchanging individuals with left, right, up, and down, with the 4 first neighbors, okay? And this is exactly the numerical approximation for the Laplacian operator. And of course, if you have 3 dimensions in space, you have to exchange individuals with left to right, up, down, front and back, yeah, in 3 directions, yeah. So the simulations, the numerical code is pretty similar, okay, but it takes a lot longer, right? Because, for instance, here I have 50 points in space, right? If I have 50 points in 2 dimensions, it's now 2,500 points, right? And if I have in 3 dimensions, I have 50 times that, right? So it's computationally grows a lot more heavy. But yeah, it's possible, and it's pretty much the same. It's computationally more intensive, but conceptually it's very similar. Yeah?
And also the interval in the animation function, do you know the units?
The GX?
No.
The interval?
In the animation function.
The animation function, yeah?
The interval.
The interval? Yeah,
yes.
I don't quite remember actually. I think it is in milliseconds. Maybe let's find out, right? So yeah. How do I find out? Just call help the function, right? So yeah. Oof. Oh, it doesn't want to run anymore. Help. Well, what is, maybe this is stuck at somewhere else. Maybe the internet has gone down, I don't know. You see that it's all disconnected. Maybe this is still running this video over here, I don't know. I don't think this is the problem. Maybe at the end here. Let's see. It's not running. Yeah, I don't know. Well, if you just type help animation this here, you'll find it's probably milliseconds or something like that, yeah. More questions? Okay, so it's the time for the class is over, right? But maybe try to find the solution for the last exercise here. And I want a natural number, right? Maybe the number will surprise you a bit. It's a kind of known number. Yeah. Okay. Sorry. Yeah. Okay. Yeah. Which patch size? The minimum size of the patch that will allow the population to not go extinct. Okay. Yeah. Sorry.
I found something around 3.26.
3.26. I think it's a little bit smaller than that. Okay, I'll not spoil this. Okay, so try to do it by yourselves and then tell me the answer tomorrow. Okay? Yeah.